Multi-fingered robotic hand is extremely effective in achieving dexterous tasks with tactile sensors. However, it is challenging to control. One of the major factors which poses the challenge is the sheer diversity of the objects involved in such tasks, which have various properties. Learning such nonlinear data is always challenging. We achieved object recognition with convolutional neural networks and tactile sensors. However, processing arbitrarily shaped tactile features with rectangular convolutional filter can be unstable. Furthermore, the convolutional neural networks are not sequence invariant, so the sequence of tactile data can change the output of the network. Graph neural networks are permutation invariant and really good at extracting morphological features, so we got good manipulation results with 8 objects. However, training the models was still difficult because of the diversity mentioned above. Furthermore, we did not really use them to their best possible extent of learning the morphological features, something we believe is extremely useful. The ability to recognize the shape and proprioceptive state of the body does help humans to achieve complex dexterous tasks, including the object property recognition, because they can accommodate for diversity in the day-to-day objects. Furthermore, the tactile perception itself is accomplished with integration of tactile states and the proprioceptive states. If the communication between the S1 cortex of the brain and the motor cortex of the brain is hampered, research suggests that the ability to perform dexterous tasks is also hampered in such people. Taking upon this idea, we propose that the knowledge of body lets the model become more accommodative to the diversity of the touch states, and hence it learns the object property and hand interaction more effectively. To produce the combined representation of the tactile and proprioceptive modalities in a graph, we propose utilizing the edges of a graph for spatial embedding, in our case the morphological features of the hand. We further propose a novel way to process such features which are associated with the same nodes of the graph but have different modalities. We evaluate our proposed method with object property recognition task to see how well it accommodates for different properties of objects. Hence, our input to the models is the proprioceptive and tactile data of 8 objects, and our output is a multi-class classifier of 6 object properties. The proposed spatial edge features are simply the Euclidean distance between the target node and its neighbor and the orientation vector of this Euclidean distance, as you can see in the blue box. These edge features can be embedded into node feature space using an edge feature encoder, which is a single layer perceptron, and then they can be used for graph convolution operations. Another way of producing morphological or topological embeddings is to use the global positions of the tactile sensors. Hence, we also produced global or absolute topological features, which are simply the distance of origin and target node and the orientation vector of this distance. We also trained models using these features for more thorough investigation. We also created a graph convolutional network architecture for the node features of the same node but dissimilar modalities in a graph. We process the features of different modalities through independent threads of graph convolutional layers, and at the end we fuse these features. We collected the manipulation data of 8 objects using Allegro hand and U-Skin tactile sensors, and then we prepared the labels of the properties which we wanted the model to recognize. In order to validate our method, we also compared it against some established baselines for tactile processing. For convolutional neural networks, we converted the tactile features and absolute morphological node features into feature maps as shown in the figure, and for the feed-forward neural network, we simply flattened the features and passed them through a multi-layer perceptron. We also trained a multi-thread CNN, an architecture similar to a multi-thread GCN. We trained GCN, CNNs, and FNNs with the 7 input combinations shown in the table, and with all the input combinations and the architectures we got total 18 models, and with and without joint angles we get 36 models. So all these 36 models were trained to evaluate the proposed method. To evaluate the performance of the proposed method, we first compared detection rates of all the models. As you can see, the proposed method, which is the MTGCN with tactile and edge features and joint angles input combination, gives the best result. More results in this table are explained in details in the paper. The size of the parameter matrix of edge encoder is number of nodes into 4 by number of edges into 4. First, we decomposed this size to number of edges by 1. Then we assigned a color map to these decomposed decomposed values. Therefore, colors of edges in the figure correspond to these decomposed features. When the joint angles are not given to the MTGCN, the network assigns higher values to the edges between the joints. This is because it needs to extract more information from these positions. When the joint angles are provided to MTGCN, we can see bluer values to the joint. This is because the MTGCN can associate the joint values to the positions of these bluer edges where the joints are. Either way, we can see that the edge encoder can detect the joints and the skin patches. Because our model has morphological features embedded in the edges of its graphs, we also decided to compare the performances of the model with different adjacency matrices of different edge densities. We can see as a general trend that with increase in edge, the accuracy of the network increases. We believe this is due to the fact that we are also providing information by the means of edges, and the more edges, the more information is given to the model. We also did TSNE analysis of the GCN features of the model, and we found that the model can recognize the topological structure of the hand, as it can separate features coming from different parts of the hand. So in conclusion, we proposed a method of utilizing the edges of graphs for spatial embedding, and we embedded the morphological features of a robot hand. We could also confirm that with the proposed method, the model can learn the locations of the joint angle on the hand. We also got an interesting result that with edge features, the models with denser graphs can produce better performance. We also exhibited the importance of combined tactile and proprioceptive representation and the effectiveness of GCNs in producing such representations over the conventional methods. And finally, we achieved the best object property recognition rate with the proposed method.